Hi, Steve Ellingson here from Virginia Tech. This is a brief introduction to our research project called Interference Canceling for Improved Coexistence Between Passive and Active Radio Systems. The problem being addressed in this research is interference to radio astronomy and other passive uses of the radio spectrum by wireless communication systems, radar, navigation systems, and other active uses of the radio spectrum. For a long time, radio astronomers have been able to contend with this interference by avoidance, that is, by not observing when the interference is present, or simply by deleting portions of an observation that are afflicted by the interference. However, this is becoming gradually more difficult as active uses of the radio spectrum continue to proliferate. We're investigating a third option for mitigation beyond avoidance and data editing, and that is to use interference canceling to provide the ability to look through the interference. The top-level concept is illustrated in the figure in the upper right. In this figure, the telescope output is x of t, and that's entering from the upper left. The telescope output consists of astronomy, that's s of t, the interference, that's z of t, and noise, that's n of t. The objective is to remove z of t without affecting s of t or n of t. To do this, we need a reference signal, and that's d of t, entering from the lower left of this figure. This signal could be from an auxiliary antenna that's pointed at the source of the interference, or it could be a signal processing model for the interference with parameters that are determined on the fly. And from that comparison, generate the signal z hat of t, which is our best possible estimate of the interference waveform. Then all that remains is to align x and z hat in time, and then subtract z hat from x. Ideally, the interference is completely removed in this operation. In practice, of course, z hat is not exactly equal to z, so instead you've succeeded only in reducing the interference and not quite eliminating it. An example of this technique is shown in the lower right of this slide. The interference being addressed in this example is a weather radio station, which is transmitting an analog FM voice signal. The image on the left shows what the telescope sees. The horizontal axis is 1 second of time, and the vertical axis is 70 kilohertz of bandwidth. We see two signals, a relatively strong signal that will attempt to cancel, and a somewhat weaker signal at a lower frequency that we'll leave alone in this example. Note that FM modulation is clearly visible in the strong signal, and being FM, it has a pretty complicated dynamic spectrum. In this example, we use the parametric signal model approach for the reference signal. Specifically, all we do is model the interference as a sinusoid with parameters for frequency, magnitude, and phase. We partition the input into short segments of time, estimate those parameters within each segment, synthesize the sinusoid, and then subtract that from the output. The result is shown on the right. You can see that the formerly strong signal has now been reduced to the level of the second weaker signal. In particular, you can see that the modulation has been suppressed to a level that is now difficult to see. However, it is also clear in this example that performance is limited. That is, we have not completely eliminated the signal. Here, this is due primarily to estimation error, which is in turn due to the low signal-to-noise ratio of the interference, and due to the limitations of the parametric signal model. The ultimate goal of our research is to render that signal undetectable in the output, so that it cannot possibly interfere with a much weaker sine signal. To make progress towards this goal, we're looking into a combination of strategies that focus on improving the quality of the reference signal, D of t. These strategies include machine learning, improved signal models, and methods in which the transmitter generating the interference cooperates with the operation of the canceller. Our efforts so far on this project suggest that these strategies can potentially yield the desired improvements. Of course, there's much more work required to develop robust algorithms that work properly in all kinds of situations, and then to properly demonstrate and quantify performance. Also, there's some additional issues to grapple with. One of these is the detection problem. Basically, if you want to cancel a signal in real time, you have to detect it immediately. Unfortunately, it turns out that interference signals are often too weak to detect promptly, and at the same time, they can be strong enough to be damaging to the radio astronomy signal. Here we think some recent developments in machine learning may be helpful. Another thing that happens in practice is that the interference estimate, z hat in the block diagram shown in the upper right, contains some additional noise and spurious content that has been generated in the process of waveform estimation. And now that extra stuff is being added to the original signal. We refer to this aspect of the problem as toxicity. Basically, a lot of effort is required to keep the canceller from injecting additional noise and spurious signals into the output. In summary, it's not sufficient merely to be able to suppress the interference. You first have to be able to detect the signal in real time, and then you have to make sure that in the process of canceling it, you're not contaminating the output. These are both problems that require a lot of additional effort to solve. That concludes this brief introduction to our project. For more information, please refer to the project website at the URL appearing at the bottom of this slide. I'll include a link in the description. Thanks for listening.